Imagine standing on the floor of a 1940s machine shop. Like, really put yourself there for a second.
Oh, the smell alone.
Yeah.
Just that heavy atomized oil everywhere.
Exactly. The air is thick. It's almost heavy in your lungs with the smell of that oil and, burning metal dust. And the noise is just this deafening, rhythmic, physical force.
Just a constant thumping and grinding. Vibrates right through your boots.
Yeah, and all around you, these massive heavy metal machines are turning out parts with microscopic precision. We are talking about the literal nuts and bolts and firing pins that will win a world war.
Right.
Now imagine that the exact same mindset that built those physical oil-soaked machines is actually the only thing that can save us from the catastrophic risks of modern artificial intelligence.
I mean, it sounds like an impossible leap, right? Going from a guy covered in grease turning a hand wheel to a neural network processing billions of parameters in some, sterile data
It
center.
really does.
But when you look at the underlying architecture of how human beings actually learn to manage terrifying, world-altering risk, it's essentially an unbroken line.
And that bridge between those two worlds is a concept called inspection over indemnity. And it actually started all the way back in the 1800s.
Yeah, a long time before computers.
Right. So welcome to this deep dive. Today, we are unpacking a really fascinating stack of academic and historical sources that analyze a single massive concept, which is Connecticut's role as the backbone of America.
It's such a tiny geographic sliver of a state, too.
Exactly. We are looking at how this tiny state became the structural catalyst for American survivability, moving from the Industrial Revolution right through World War II and up to the modern AI arms race.
What we're really looking at here is the architecture of trust. We're tracing how a localized culture of absolute precision and an almost obsessive intolerance for systemic failure translates from the physical world into the digital world of algorithms.
Okay, so let's unpack this for you all listening, because to understand how we survive the AI revolution, we actually have to start with steam.
We do. Mid-19th century.
Right, the Industrial Revolution is roaring, and steam power is the absolute bleeding edge of technology. It's revolutionizing manufacturing, railroads, shipping, everything. But there is a massive, terrifying catch.
A completely horrifying catch. The prevailing hazard of that era is the catastrophic boiler explosion.
And we need to be clear about what that actually means mechanically, right?
Yeah, because when water turns to steam, it expands to something like 1,600 times its original volume.
Mm.
You're essentially trapping a continuous roaring bomb inside a riveted iron shell.
Just waiting to go off.
Right. And if the water drops too low, the iron overheats. Then, when water is reintroduced, it flashes into steam so violently that the pressure spikes way beyond what the metal can actually hold.
And the metal just rips apart.
It completely shreds. And the resulting explosion releases all that stored energy in a millisecond. Shrapnel, scalding water, concussive force. It would instantly level entire factories.
Wow.
We are talking about explosions happening roughly once every 4 days across the United States.
Once every 4 days. The human cost of that is mind-boggling. I mean, I was looking at the details of the Sultana steamboat disaster of 1865 in our sources.
Oh, the Sultana. Yeah, that's a grim one.
It really is. The Civil War has just ended. You have this wooden steamboat on the Mississippi River, packed with returning Union prisoners of war.
Just thousands of men trying to get home.
Exactly. And they patched a leaking boiler with a piece of metal that wasn't thick enough just to keep moving. And the boiler blew, causing a chain reaction. Over 1,800 people died in the middle of the night.
It remains the worst maritime disaster in U.S. history. Worse than the Titanic.
That is wild.
And what is vital to understand for our conversation about AI today is society's mindset at the time of the Sultana.
Yeah.
Society had a deeply fatalistic approach to steam technology.
What do you mean by fatalistic? Like they just accepted it?
Exactly that. Boiler explosions were widely categorized as acts of God.
Wait, really?
Yeah. The prevailing thought among business owners, politicians, and the public was simply that if you harness the miraculous power of steam, occasionally the beast is going to wake up and kill you.
That is, I can't even wrap my head around that.
It was treated as a natural disaster, like an earthquake or a hurricane. You can't prevent it, You can only pray it doesn't happen to you and clean up the bodies when it does.
It's like ancient people watching a solar eclipse and thinking the gods are angry, completely unaware that there are just, orbital mechanics at play. They just thought, well, the boiler exploded, God willed it.
Right. Until 1857. That's when a group of incredibly forward-thinking individuals formed the Polytechnic Club of Hartford.
Okay, who are these guys?
They were engineers, scientists, businessmen. And they initiated a really profound epistemological shift. They looked at the blackened craters of these factories and said, these are not acts of God. These are engineering failures.
And an engineering failure inherently has an engineering solution.
Exactly. Stop blaming the universe. Start checking your pressure valves and the thickness of your iron.
That makes so much sense.
And that radical shift in thinking led directly to the founding of the Hartford Steam Boiler Inspection and Insurance Company, HSB, in 1866.
Okay, HSB.
Yeah, and HSB changed the financial world forever because they built a business model on a logic that was entirely revolutionary for the time. Their motto was inspection over indemnity.
Okay, let's break that down for the listener. Indemnity is the payout, right? It's the insurance company cutting a check to the widow or the factory owner after the place burns down.
Correct. Traditional insurance just absorbs the risk of the disaster and redistributes the financial pain. HSB inverted the model entirely.
How so?
They made the financial instrument, the insurance policy, completely subordinate to the safety instrument, which was prevention and engineering inspection.
Oh, wow.
They realized that catastrophic risk could be converted into an auditable, inspectable standard of care.
So they are operating upstream. They're saying, we aren't just going to wait downstream for the boiler to blow and then pay you. We are going to send an inspector into your basement, and if your metal is too thin, we won't insure you at all.
Yes, and in systems engineering, that is the very definition of an assurance layer. You prove your systemic reliability before you are allowed to operate.
It makes me think of, like, modern car insurance. The previous mindset was assuming car crashes are just inevitable bad luck, a fact of life.
Right, just pay out the claim when it happens.
Yeah. HSB essentially invented the concept of the vehicle safety inspection, but for boilers. They refused to give you the financial protection unless you proved you'd done the engineering homework.
That's a great analogy.
Mhm.
And this highly localized practice in Connecticut evolved into what became known as the Hartford Standard.
And how far did that spread?
Well, HSB's internal engineering specifications for what made a safe boiler were so rigorous and so effective at preventing deaths that they eventually formed the basis for the 1914 ASME Boiler and Pressure Vessel Code.
Which is still used in over 100 countries today,
To
right?
this day.
That's crazy. A group of guys in Hartford in the 1800s literally wrote the rule book for global industrial safety because they refused to accept that machines had to randomly kill people.
It's a huge legacy.
But here's where I get stuck. It is one thing to send an inspector into a basement to look at a single boiler with a flashlight. How does this mindset actually scale?
That's the big question.
Right, because when we get to the 1930s and 40s, we aren't just talking about keeping a few factories safe. We are talking about outfitting an entire global world war. You can't just scale insurance policies to win a war. You have to scale the physical precision itself.
You're hitting on the exact pivot point of the sources. To see that scaling in action, we have to travel from the insurance offices of Hartford to the manufacturing floors of Bridgeport.
Okay, take us to Bridgeport.
That exact philosophy, demanding structural safety and having zero tolerance for systemic failure, is what laid the groundwork for Connecticut's precision manufacturing ecosystem.
And to understand how they achieved that scale, we have to look at an invention that is arguably the ultimate World War II capability multiplier.
Let's talk about Rudolf Bayernow.
I love this guy's story. It's 1936. He's a Swedish immigrant living in Bridgeport, Connecticut. He runs a pattern shop, basically making wooden models for metal castings.
A very hands-on guy.
Very. And the legend goes that he's sitting in his delivery truck waiting for a client, and he sketches a design for a new machine on the back of a paper bag.
Just a paper bag sketch.
Yeah, and that sketch becomes the Bridgeport vertical turret milling machine.
The Bridgeport Mill.
Okay,
To anyone outside of manufacturing, it just looks like a heavy chunk of gray metal.
really unassuming.
But within industrial history, it is almost impossible to overstate the importance of this machine.
Well, the first one shipped in August of 1938, right before the war kicked off, and it cost $995. But what I want to understand is why it was so revolutionary. What was milling like before this paper bag sketch?
Before the Bridgeport, milling machines were massive, rigid, horizontal behemoths.
Like, how massive?
Huge and incredibly unwieldy. If you wanted to cut a complex shape out of a block of steel, say, cutting a slot at a 45-degree angle, the cutting tool was fixed in place.
Okay, so the tool doesn't move.
Right. So the machinist had to physically unclamp the heavy steel workpiece, calculate the geometry, insert little metal shims to tilt the piece to exactly 45 degrees, clamp it all back down securely so the vibration wouldn't ruin it, and then make the cut.
That sounds incredibly tedious, like you're adjusting the metal to the machine, not the machine to the metal.
Exactly. A machinist could easily waste 3 hours just setting up a piece of metal for a cut that would take 5 seconds to actually perform.
Wow.
It required decades of tacit knowledge. You needed an absolute master machinist just to set up every single discrete task.
So Bannow looks at this process and basically realizes the machine is backwards.
He did. The Bridgeport Mill introduced 4 specific innovations that completely inverted the paradigm.
Okay, let's go through them. What was
Right.
the first?
First, the quill. This allowed the spinning cutting tool to be advanced vertically with a hand lever, exactly like a standard drill press.
Okay, so a motion every mechanic already understood in their bones.
Exactly. Second was the turret. This is the big one.
Massive, right?
Huge. The turret allowed the entire head of the machine, the part holding the spinning cutter, to rotate and tilt.
Oh, I see where this is going.
Yeah. So instead of the machinist spending 3 hours unclamping and shimming that block of steel to get a 45-degree angle, they just left the steel clamped flat.
And they move the machine instead.
Right. They just loosened a bolt, tilted the head of the machine to 45 degrees, and made the cut.
You just saved 3 hours. It's like having a multi-tool where the head pivots instead of carrying a massive toolbox and constantly changing your stance.
Precisely. Then you have the third innovation, the ram. This was a sliding arm that let the machine head reach much further out over the table, accommodating much larger parts.
Makes sense. And the fourth.
Finally, the R8 taper. This was the specific tapered shape of the hole where the cutting tools were held.
Why was that a big deal?
Because Band now designed it so elegantly that it became a universal standard across the entire global industry. You could buy an end mill cutter literally anywhere in the world, and it would fit a Bridgeport.
So Bannow didn't just invent a machine, he really invented a platform. But how does this translate into winning a war? Because that's the big claim here.
To understand the strategic impact, we have to look at a principle in manufacturing called the tolerance stack.
The tolerance stack.
Yeah, it's foundational to modern quality standards, like AS9100 for aerospace.
Break down the tolerance stack for me. How does it work?
Think of a complex system, like a Pratt & Whitney aircraft engine. It has thousands of moving parts. The systemic output quality of that engine is determined by its worst performing component.
Like a chain is only as strong as its weakest link.
Exactly.
Yeah.
Let's say Pratt & Whitney machines their main crankshaft to a tolerance of 1/1000th of an inch. Absolute perfection. But they rely on a tiny subcontractor in a garage in New Haven to supply a small retaining pin.
And the guy in New Haven has old, sloppy equipment.
Right. So his pin is off by, say, 5/1000ths of an inch. When that engine is running at 3,000 RPMs over the Pacific Ocean, that tiny dimensional error creates a microscopic vibration.
Oh, no.
Yeah. That vibration propagates through the entire engine block. The tolerance error stacks up, bearings fail, the engine seizes, and the plane goes down.
Just because of one pin.
Exactly. The entire system's precision sealing is dictated by its weakest link.
It doesn't matter how good the massive defense contractor at the top of the chain is if the thousands of little mom-and-pop machine shops supplying the bolts and brackets are churning out garbage.
That's the issue. And before the Bridgeport Mill, raising the quality of those mom-and-pop shops was basically impossible. There simply weren't enough master machinists to go around, and complex machines were way too expensive.
So the Bridgeport democratized precision.
It did. It allowed a small shop with a less experienced operator, someone who maybe only had a few months of training, to perform highly complex, high-tolerance machining.
So it raised the baseline precision of the entire country. Now, the research analyzes this machine using a specific cognitive framework called Intelligize.
Yes, developed by Transcendent Intelligence Technologies.
I want to push back on this a bit because, I'll be honest, Intelligize sounds heavily like corporate trademark jargon. What does this framework actually teach us about a hunk of metal?
I get that. It's a fair critique of the terminology. But the framework itself is actually highly useful for cutting through exactly that kind of industrial blindness we tend to have.
What do you mean by industrial blindness?
We usually look at machines just in terms of horsepower or speed. The Intelligize framework forces us to look at human coherence across 5 distinct domains. It explains why the machine was adopted so universally.
Okay, walk me through these human factors. What's the first domain?
First is the logical domain. The Bridgeport achieved logical coherence because the physical motions required to operate it were intuitive.
Like the drill press lever.
Exactly. Pulling the quill lever felt natural. It reduced the cognitive load on the operator. When the operator doesn't have to fight the machine's logic, they make fewer errors.
Makes sense, like a well-designed smartphone interface. What's the second domain?
The ethical domain.
Hmm.
By democratizing precision, the Bridgeport made high-tolerance operations accessible to more people.
How is that ethical, though?
Well, in the context of the 1940s, this meant the capacity to contribute to defense production was distributed to a vastly broader labor pool.
Oh, because the men were drafted.
Right. As men went overseas, millions of women entered the manufacturing workforce. The intuitive design and accessible precision of the Bridgeport ethically empowered this new workforce to immediately produce life-saving defense materials without needing a 10-year apprenticeship.
I hadn't thought about that. You really can't mobilize a whole society if the tools of production are gatekept by a tiny elite fraction of the population.
Exactly. Third is the emotional domain.
Emotional for a machine.
Yes, this is something engineers often ignore, but machinists didn't just use the Bridgeport, they loved it. It generated fierce professional loyalty.
Really?
Yeah, there was a pride of accessibility. Tools that resonate emotionally with their users. Tools that put the user in a flow state simply produce better, more consistent outcomes than tools that are functionally equivalent but frustrating to use.
Okay, I can see that. Fourth is the intuitive domain, which goes back to Banno's paper bag sketch, right?
Right. He observed a shop floor frustration, the 3 hours of clamping and unclamping, and he intuitively synthesized a complete architectural solution in one sketch.
He didn't just tinker with a minor attachment, he rethought the geometry of the work.
Exactly. And finally, the temporal domain. The timing was historically impeccable.
Because it came out in 1938.
Yes. The mill arrived on the market right before the war. By the time the absolute peak of wartime production demands hit in 1941 and 1942, the machine had already established its reputation and embedded itself deeply into the supply chain.
So the stars perfectly aligned. Now, the analysis goes one step further into the jargon forest with something called MDMS.
Multidimensional math synchronicity.
Yeah, and again, I have to be honest, that sounds like a spell from Harry Potter. What does that actually mean for the guy standing on the shop floor?
Let's strip away the corporate phrasing. Multidimensional math synchronicity is just a way of measuring when a system achieves harmonic convergence.
Harmonic convergence.
Right. It's when all the different variables of a problem suddenly align to solve each other. The Bridgeport mill represents this in physical reality.
Okay, give me an example of these variables aligning.
Sure. First, you have numeric convergence. The machine's calibrated tolerances, the exact math of its lead screws, perfectly match the mathematical demands of wartime blueprints.
Okay, so the math lines up. What's next?
Second, symbolic convergence. Bridgeport literally became the generic noun for all vertical mills.
Oh, like calling all tissues Kleenex?
Exactly. It became the symbol of milling itself. Third is logical ethical convergence.
Which means what?
Usually in engineering, there is a strict trade-off. You can have high precision, or you can have high accessibility for amateur users. You rarely get both.
Right.
The Bridgeport mathematically optimized both simultaneously. And finally, energetic convergence.
Meaning the output versus the cost?
Exactly. For a remarkably low $995 investment, the energetic output, the sheer volume of high-value parts produced over decades, was astronomically out of proportion to the initial cost.
Okay, translated out of the jargon, that makes total sense. We are basically saying the Bridgeport Mill was the technological platform that allowed regular, everyday people to download precision capabilities. It really was the iPhone of 1938.
A perfect analogy. Without this platform of precision democratized across the capillary system of small machine shops, the massive defense contractors would have completely collapsed under their own weight.
Because it wouldn't have the parts.
Right, they would have had the raw steel, but the supply chain would have choked to death on a lack of precision parts.
Which brings us to the actual output of this system. Let's look at Connecticut's role as the WWII backbone, because the numbers here blow my mind.
They are staggering.
Connecticut accounted for roughly 4.1% of all U.S. military armaments. They ranked 9th in the nation for total output. And this is a state you can literally drive across in 2 hours.
It's incredible. And it's not just the sheer volume, but more importantly, the complexity of what they produced.
Give us some examples.
Well, you have Pratt & Whitney in East Hartford producing over 300,000 aircraft engines.
300,000.
Yeah. And to put that in perspective, those exact engines powered 96% of all military transport planes during the war.
96%. That is unbelievable.
It really is.
If you were flying troops, supplies, or blood anywhere in the world, from the Pacific Islands to the European theater, you were relying on Connecticut engineering.
Absolutely. Then you have Electric Boat down in Groton building 74
And a
submarines.
submarine is no joke.
No, we need to pause and appreciate the engineering of a 1940s submarine. It is one of the most complex mechanical environments on Earth.
Seriously.
You are building a high-pressure steel tube meant to sink hundreds of feet underwater, withstand crushing oceanic pressure, and house dozens of men, batteries, diesel engines, and explosives.
Wow.
It is a life-or-death system where a single faulty valve means 80 men drown in the dark. There is absolutely zero room for the tolerance stack to fail.
And they built 74 of them. Plus, you've got Colt and Winchester pumping out millions of small arms, Sikorsky innovating the R-4, which was the world's first mass-produced helicopter.
Exactly. Now, consider the counterfactual analysis that historians apply here in the sources.
What's counterfactual?
They ask the question, what if Connecticut simply didn't step up? What if that 4.1% wasn't there?
The conclusion isn't that America would have immediately lost the war, right? Because the industrial base of Detroit and Chicago was still massive.
True, the Allies likely still win. But the counterfactual argues it would have been a much longer, vastly riskier, and infinitely more fragile war.
How so?
If you remove Connecticut, aircraft logistics slow down to a crawl because you lose 96% of your transport engines. Naval attrition in the Pacific drastically increases because you don't have the Groton submarines choking off Japanese shipping lanes.
But the research points out something else that would happen if Connecticut disappeared. It says industrial accidents nationwide would have spiked.
Yes.
Why would an ammunition plant in Ohio suddenly have more accidents just because Connecticut wasn't making parts? I don't get the link.
Because of the other half of Connecticut's DNA. We just talked about the manufacturing side, Bridgeport and East Hartford, pushing the physical limits of precision.
Right.
But the other half is the insurance side, the legacy of the Hartford Standard and HSB. The Hartford insurers were the ones underwriting the massive chaotic risks of total industrial war.
Underwriting the war, what does that actually look like in practice?
It means providing the financial backstop for government war risk programs. The U.S. government was asking factories to handle millions of tons of high explosives to work 2047 to hire untrained workers.
So the risk of factories blowing up was astronomical.
Exactly. Our historical data even notes that Hartford insurers quietly underwrote risks associated with the Manhattan Project.
That is insane to think about. Actuaries trying to price the insurance premium on the creation of the first atomic bomb.
I know, right? But they didn't just sit in offices and sign checks. Just like HSB inspecting those steam boilers in the 1800s, these Hartford insurers deployed armies of safety engineers directly onto factory floors across the entire country.
Oh, so they were hands-on.
Very. They mandated hazard mitigation, they enforced fire codes, ventilation standards, and machine guarding. They carry that Connecticut culture of inspection over indemnity to every state in the Union.
I love this synthesis. If we look at the war effort like a modern tech company, Connecticut was the ultimate back-end developer.
Oh, that's a brilliant way to phrase it.
Right. They built the server infrastructure, the data pipelines, the security protocols. They built the unseen architecture that kept the front-end user experience, which unfortunately was the actual bloody battles being fought from crashing due to systemic failure.
I think back-end developer is the perfect framing. The synergy between the manufacturing sector demanding absolute physical precision and the insurance sector demanding absolute risk accountability created a very unique failure-intolerant DNA in the state.
Failure intolerant.
Yes. And the reason we were spending so much time analyzing this historical back-end developer role is because building infrastructure that prevents systemic collapse is precisely what the world desperately needs right now as we face artificial intelligence.
Okay, here is the big jump.
Yeah.
We are moving from the physical back-end to the digital back-end, from the 1940s machine shop into the 2020s data center.
The stakes are just as high.
But I hear this comparison to steam boilers, and I genuinely struggle with it. A boiler is physical metal. I can hit it with a wrench. And AI is billions of floating data points inside a server. Aren't we just pretending we can inspect something that is mathematically invisible?
It's the defining question of our era, really. To answer it, we have to look at the fundamental clash of systems happening right now.
What clash?
We have AI systems, which are inherently probabilistic,
Yeah.
and we are embedding them into institutions that are inherently deterministic.
Let's go deep on that math. Probabilistic versus deterministic. Break that down.
Sure, a deterministic system is one where a specific input always yields an exact, guaranteed output. 2 plus 2 equals 4. A physical pressure valve opening at exactly 100 psi.
Okay, predictable and fixed.
Right. Institutions like insurance claims processing, defense procurement, mortgage underwriting, and healthcare triage. These are deterministic domains. They require absolute legal and operational certainty.
You are either approved for the mortgage or you are denied. Your medical claim is valid or it is fraud. Black and white. Exactly, black and white. But AI, specifically machine learning and neural networks, does not think in black and white. It is probabilistic.
It's guessing.
It is essentially a highly sophisticated casino calculating odds. It looks at a medical chart and it doesn't say, this is cancer. It says, based on my training data of 2 million previous charts, I am 87.4% confident that these pixel arrangements represent cancer.
Okay, so when you force a probabilistic engine, an AI making an educated guess to make a deterministic decision like actually canceling someone's health insurance,
Yeah.
you introduce a massive liability.
Yes, you introduce what is identified in the research as unknown truth.
On truth, that sounds incredibly dystopian. Give me a real-world scenario of unknown truth.
Okay, imagine an algorithm denies a critical medical claim for a patient. The patient calls the insurance company and asks why.
And what does the company say?
The human claims adjuster doesn't know. They just looked at the screen, saw the red denied box, and trusted the software.
So they passed the buck. Right, so the patient's lawyer contacts the software vendor. The vendor says, well, it's a proprietary neural network that dynamically adapts, so we can't explicitly trace the exact logic path it took to deny this specific claim.
So everyone points the finger at the math. Nobody takes responsibility.
Exactly. Suddenly, no human being, no corporate entity, and no developer legally or operationally owns the risk of that decision. It is enforced upon the patient as a deterministic fact, but it has no verifiable lineage.
That is horrifying. It is the modern equivalent of the act of God excuse for the exploding steam boiler. The algorithm did it. It's a black box. We can't explain it. Sorry for your loss.
Precisely. And just like the Polytechnic Club in the 1850s, we desperately need an epistemological shift. We need to say, these are not acts of the algorithmic gods. These are engineering systems, and they must have engineering accountability.
And this is where modern governance frameworks are trying to step in, right? Like the NIST AI risk management framework that ALRM.
Yes. NIST is doing crucial work there.
It's attempting to formalize trustworthy AI as a continuous lifecycle discipline. It's not just slapping a safe sticker on a software box. It's a continuous process to govern, map, measure, and manage the risk.
Yes. And the insurance industry is stepping up to lead this, just like they did with boilers. The National Association of Insurance Commissioners, the NAIC, released a model bulletin setting very strict expectations for how insurers use AI.
What are they demanding?
They are demanding accountability, transparency, and fairness. And crucially, Connecticut adopted this via Bulletin No, MC25, in February of 2024. They officially put a stake in the ground.
But I keep coming back to the enforcement part. Critics of AI regulation consistently say that AI is inherently a black box.
They say that a lot.
Yeah, they say if you try to regulate it, you'll just stifle innovation because it's technically impossible to map out exactly how a dynamic neural network makes every single decision.
Yeah.
Are they right? Are we asking for the impossible?
No, they are not right. The black box excuse is heavily motivated by institutional interests.
You mean tech companies?
Yes, tech companies who simply prefer not to assume the legal liability of being regulated. It is a corporate shield, not a technical reality.
Wow.
To prove that establishing lineage is technically possible, we just have to look at how software supply chain transparency has evolved over the last 3 years, specifically through something called an SBMOM.
Okay, an SBOMI. That stands for Software Bill of Materials. It gained massive traction after Executive Order 420-228, which mandated them for anyone selling software to the federal government.
Correct. Let's say you buy a piece of enterprise software. It isn't just written from scratch by one guy in a basement.
No, it's a patchwork.
Right. It is stitched together using hundreds of different open source code libraries and third-party dependencies. An SBOM is a formal, machine-readable inventory of every single component inside that software.
So if a massive cybersecurity vulnerability is discovered in some random, widely used piece of open source code, you don't have to scramble in the dark wondering if your company is exposed.
Exactly.
You instantly check your SBOM. If that vulnerable code is on your list, you patch it.
Exactly.
Mm-hmm.
So take that exact concept of inventory and extend it to artificial intelligence. Get the AI BOM, an AI bill of materials.
And what does that do?
This provides a complete, auditable inventory of the AI system.
What exactly goes into an AI bomb? Like, what are they tracking?
It documents the model lineage. So where did the base model come from? Was it a llama model? A GPT variant?
Okay.
It documents dataset provenance. What exact data was used to train it? Were there copyrighted materials? Was the data ethically sourced?
That's huge for legal reasons.
Oh, absolutely. And it logs the specific training parameters, the weights, the biases, and all external software dependencies.
So an AI bomb is basically a nutritional label for an algorithm. It doesn't force the developer to publish their highly guarded proprietary secret recipe on the internet, but it definitively tells me if there are peanuts in the code. It tells me the ingredients.
That is the perfect way to conceptualize it. And it proves that establishing decision lineage at the inference layer, the exact millisecond the AI makes a decision, is technically achievable right now.
We can actually do it.
Yes. You can timestamp and log the exact state of the model, the data it referenced, and the inputs that led to a specific output. The transparency is scientifically possible. It's just a matter of having the willpower to mandate it.
But mandating it requires a very specific kind of culture. You can't just slap a new regulation on a Silicon Valley startup whose motto has always been move fast and break things and expect perfect compliance. They don't have the mindset for it.
They really don't.
And this brings us to one of the most fascinating parts of the deep dive: high reliability organization theory, or HRO theory.
HRO theory is the sociological key that unlocks this entire problem. It was developed by organizational psychologists Carl Wick and Kathleen Sutcliffe.
What were they trying to figure out?
They wanted to understand a specific paradox. How do organizations that operate in environments of extreme hazard where the cost of a single failure is catastrophic manage to operate with near-zero error rates?
We are talking about nuclear power plants, right?
Mm-hmm.
Air traffic control towers, U.S. Navy aircraft carriers, places where you can't just issue a software patch if something goes wrong, because going wrong means a reactor meltdown or a mid-air collision.
Precisely. Wick and Sutcliffe embedded themselves in these environments and identified 5 core principles that define an HRO culture. And as we go through them, contrast this with the typical culture of a fast-moving tech startup.
Okay, let's hear them. What's the first principle?
First is a preoccupation with failure. Most companies celebrate their successes and bury their mistakes. An HRO obsesses over its near misses.
Give me an example of that.
If an aircraft carrier deck crew has a procedure where 2 jets almost clip wings, they don't say, "Phew, good thing they didn't hit." They shut down operations and treat that near miss as a symptom of a massive systemic disease.
Wow, that is intense. Okay, second principle.
Reluctance to simplify. In a normal company, if a project fails, they find a scapegoat. Oh, Dave in accounting made a human error.
Right, blame Dave.
An HRO refuses easy explanations. They dig into the system. Why did Dave make the error? Was the dashboard confusing? Was he fatigued? They embrace the complex reality of the system.
Third.
Sensitivity to operations. Leadership in a typical corporation only looks at high-level, aggregated dashboards.
Spreadsheets and charts.
Exactly. In an HRO, leadership maintains a constant granular awareness of what is actually happening on the front lines. The admiral knows exactly what the guy turning the wrench is dealing with.
Fourth is a commitment to resilience.
Right. Normal companies assume their plans will work perfectly. HROs know that eventually, despite all their obsessive preparation, a novel failure will occur.
Something they never planned for.
Yeah. So they train relentlessly not just to prevent errors, but to detect, contain, and rapidly bounce back from failures before they cascade into total system collapse.
And the final principle.
Deference to expertise.
Yeah.
This is the most crucial one. In a normal company, the person with the highest title makes a final decision.
The CEO gets the final say.
Right. But in an HRO, during a crisis, the rigid hierarchy instantly dissolves. Decision-making authority migrates directly to the person with the most relevant operational expertise, regardless of their rank.
So the expert takes over.
Yes. If a junior radar operator on a ship spots an anomaly, the captain defers to the operator's expertise to interpret it.
Now here is the absolute genius of the analysis we are unpacking. The researchers take HRO theory and map it directly onto Connecticut's historical precision manufacturing culture. Think about that machinist in Bridgecourt during WWII, or a modern machinist in East Hartford making parts for a jet engine today.
The mapping is flawless. A machinist operating to AS 9100 aerospace standards embodies all 5 of those HRO principles every single day.
They really do.
They're deeply preoccupied with dimensional failure, measuring their cuts constantly. They refuse to simplify a tolerance error. They are intensely sensitive to the operations, feeling the vibration of the cutter, listening to the pitch of the metal. They build resilience into their tooling setups. And on a healthy shop floor, if a frontline 20-year-old machinist says a part is out of spec, the plant manager defers to their expertise and stops the production line.
So HRO theory is essentially proving that the people who should be writing the rules for AI shouldn't be politicians sitting in a vacuum in Washington, and it shouldn't just be software engineers in Silicon Valley.
No, it shouldn't.
It should be the machinists of the data world, the actuaries, the safety engineers, the people who have spent a century understanding physical risk. Connecticut's historical industrial DNA is literally HRO DNA applied at a massive statewide level.
It is the cultural substrate required to make governance real. If you try to implement an AI bomb in a culture that doesn't fundamentally care about failure, a culture that views compliance as an annoying speed bump, it just becomes a meaningless check-the-box exercise.
But if you implement that requirement in a culture defined by the Hartford Standard,
A culture of inspection over indemnity, yeah, then it becomes a rigorous operational reality.
so this leads to the ultimate geopolitical question in our sources. If the technical tools exist, we know AI bombs are possible, and the cultural DNA exists right here in Connecticut. What happens if Connecticut actually pulls the trigger? What happens if they aggressively regulate this space and mandate upstream governance?
To understand what happens, we have to look at the economic gravity of standard setting. There's a concept in political science known as the Brussels effect, theorized by Anu Bradford.
The Brussels effect.
Yeah. It explains how the European Union is able to dictate global market standards without needing to pass global laws or treaties.
Because their internal market is so incredibly massive and wealthy, right? If you want access to European consumers, you play by their rules.
Exactly. The EU passes a strict data privacy law like GDPR. A multinational tech company based in Seattle wants to operate in Europe.
So what does the company do?
Well, it is economically irrational for that company to build one highly secure software architecture for Europe and maintain a second, sloppier architecture for the US and Asia. The overhead cost of maintaining separate compliance profiles and separate code bases is vastly higher than just adopting the strictest European standard globally.
So the EU standard becomes the global standard by default, just through market gravity. And we have a domestic version of this too, right? The California effect.
Precisely. California sets incredibly strict car emission standards. Ford and GM don't want to design a California engine, a Texas engine, and a Florida engine.
Right. That would be a nightmare for manufacturing.
So they just design all their vehicles to meet California's strict standard, and the whole country gets cleaner cars as a result.
Now, apply this market gravity to AI and the insurance industry. If the Connecticut Insurance Department, leveraging its historical status as the insurance capital of the world, steps up and mandates rigorous upstream AI governance,
It changes everything. If Connecticut mandates that any insurer operating within its borders must utilize AI bombs, maintain inference logs, and prove clear decision lineage for their underwriting algorithms.
every major insurer operates across state lines. A massive national insurance carrier isn't going to build a Connecticut-only AI system where they track lineage while using a black box system for the other 49 states.
No, they won't.
Yeah.
They will upgrade their entire national algorithmic infrastructure to meet Connecticut's baseline standard. Through market gravity, Connecticut becomes the de facto national standard bearer for trustworthy AI in finance and insurance.
But there is a massive risk here, the risk of hesitation. What happens if Connecticut sits on its hands and waits to see what the federal government does?
The term used in strategic analysis is institutional displacement. If Connecticut does not lead, it ceases to be a rule maker and becomes a rule taker.
A rule taker, meaning somebody else, the EU, California, or bureaucrats in Washington, writes the rules based on their distinct values, their risk tolerance, and their local industries. And Connecticut just has to swallow it.
And the consequences of being a rule taker are severe. First, the state's industries accumulate that governance debt we discussed earlier.
Right.
Insurers and defense contractors face mounting, unbounded legal liability from operating opaque systems. Second, you suffer catastrophic workforce leakage.
People will just leave.
Yes. The top AI talent, the elite safety engineers, the forward-thinking compliance startups, they aren't going to stick around in a regulatory vacuum. They will migrate to jurisdictions where the infrastructure of trust is actively being built and funded.
But the tools to build that infrastructure are already sitting in our lap.
Right.
The The research brings up transcendent intelligence technologies, or TSI. They developed something called UICP, the Universal Intelligence Contextual Protocol.
Right.
Without getting bogged down in the acronym, what they're offering is a real-time, upstream governance architecture that actually satisfies all these needs.
Good.
It tracks the lineage, it builds the AI BEM, it audits the decisions as they happen. It isn't theoretical vaporware. The technology to enforce the Connecticut standard exists today.
It does. And this is where the synthesis of everything we've discussed today becomes so powerful. If we apply that MDMS framework, that harmonic convergence we talked about with the Bridgeport Mill, but we apply it at a statewide jurisdictional level, we see that Connecticut has the potential for a profoundly rare historical moment.
Break down that state-level convergence for me. How do the variables align today?
Numerically, Connecticut possesses over 160 years of highly refined actuarial data and a safety code, the ASME standard, that is actively utilized in over 100 countries. The underlying mathematics of physical risk are deeply embedded in the state's institutions.
And symbolically.
Symbolically, they possess the foundational principle of inspection before indemnity. It is the most powerful symbol of trust in the financial sector.
And the logical ethical convergence.
It is the realization that you don't have to choose between having powerful, cutting-edge AI and having fair, accountable AI. With upstream governance protocols like UICP, you optimize both simultaneously.
Best of both worlds.
Exactly.
Yeah.
You protect the consumer from algorithmic bias while allowing the business to deploy AI safely. And finally, energetic convergence.
This is the most important one to me, because building new government agencies is exhausting and expensive.
But Connecticut requires absolutely no new institutional architecture to pull this off.
None at all.
None. The insurance department is already fully operational and respected. The advanced manufacturing and defense-based electric boat, Pratt & Whitney, is already there, operating as high-reliability organizations.
Wow.
The academic partnerships are already forming. The energetic cost to implement this is incredibly low compared to the massive global impact it would have.
The server is already built. It's plugged into the wall. The software is loaded. It just needs the political will to turn the key.
Exactly. Connecticut doesn't need to invent a brand new system out of thin air. It just needs to look in the mirror and realize that AI risk is simply the 21st century equivalent of a steam boiler.
I love that.
It is a terrifying new technology presenting a very old problem: probabilistic risk that demands an auditable standard of care.
So we are sitting on a massive invisible goldmine of risk intelligence, and the choice is utterly binary. Either we write the rules of the road for the next century, based on 160 years of keeping submarines from imploding, aircraft engines from failing, and factories from burning down, or we sit back, let someone else write the rules, and we just become passive passengers in our own economy.
That is the exact strategic reality. The failure-intolerant DNA that won the Second World War is the exact DNA required to govern the algorithm.
As we wrap up this deep dive, let's trace the epic through line we've walked today. We started in the 1860s, looking at the horrifying reality of exploding steam boilers that birthed the Hartford Standard, the radical, world-changing idea that we should inspect the engineering before we insure the hazard.
An incredible paradigm shift.
We moved to a paper bag sketch in the 1930s of the Bridgeport Mill, a machine that democratized precision, eliminated the tolerance stack errors, and became the physical backbone of the World War II arsenal.
The iPhone of its day.
Right. And we brought it all the way to the modern data center, exploring how AI bombs, high-reliability organization theory, and TSI's frameworks give us the exact blueprint to govern the probabilistic chaos of tomorrow. Connecticut's true legacy isn't just making physical things, it is inventing the architecture of assurance.
It's a 160-year legacy of turning the ungovernable into the reliable.
So I want to leave you, the listener, with a final thought to mull over. We've talked a lot about corporate liability and national standards, but let's bring it down to the personal level.
Yeah, how it impacts the individual.
Next week or next month, an algorithm is going to make a decision about your life. It might deny you a mortgage, or it might flag a medical chart and alter the treatment your doctor recommends.
It's happening right now.
When that happens and you realize the system can't explain why it made that choice, consider how this changes the legal definition of human negligence in America.
Oh, that's a chilling thought.
In 5 years, if a doctor blindly trusts an unauditable AI and makes a fatal mistake, will the courts treat that as medical malpractice simply because the doctor didn't demand to see the AI BM? We've spent a century learning how to prevent machines from physically breaking our bodies, but as the algorithms take the wheel, the definition of liability is shifting from the machine maker to the machine user. The technical blueprints to demand transparency exist. The only question left is, Will we demand to see the ingredients before we swallow the pill? Thank you so much for joining us on this deep dive.